purpose of this video is to introduce you to the concepts of total internal reflection and the critical angle. We're starting with a question today. When light travels from a medium with a higher index of refraction to a lower index of refraction, what happens to that light? Ideally, you answered that the light bends away from the normal, or perhaps toward the surface. Or maybe your answer had something to do with the angles that were created. The fact that the angle of refraction would be greater than the angle of incidence. This is what we've learned previously in class. So let's look at a diagram of that happening. If I focus on that diagram on the left here, we notice that the light beam that goes straight up doesn't bend at all. That's because the angle of incidence is 0 degrees. And we know that when the angle of incidence is 0 degrees, there's no refraction. However, if I take a look at this beam of light that makes an angle of incidence of 15 degrees with the normal, you can't see it on this diagram, but the normal would be drawn in like this, and this would be my 15 degrees. My refracted beam then makes an angle of 20 degrees with the normal. Going one over where my angle of incidence is 30 degrees, my angle of refraction is then 42 degrees. Notice that as I continue increasing my angle of incidence, my angle of refraction keeps increasing at a greater rate. You can see that with this diagram on the right here where these angles are marked. So that angle of incidence is 20 and the angle of refraction is 27. When the angle of incidence is 30, the angle of refraction is 42. Eventually we get to a point that the angle of refraction is all the way up at 90 degrees. If that's the case, then that beam of light, which I'll trace here in blue, it never actually leaves that first medium. It kind of refracts along the surface of the two. And then any angle above this angle, which as you see it's marked here called the critical angle, also causes that total internal reflection. So like this beam that we see right here that makes an angle of incidence of 60 degrees with the surface, it reflects off at 60 degrees, but never actually comes out into the air up here. That's total internal reflection. So again, breaking down the name of that term, my beam is totally reflecting and nothing refracts out into that second medium. Now, as we saw in the previous diagram, there's this angle called the critical angle, which is the minimum angle of incidence that causes total internal reflection. An important note is that any angle of incidence that's above the critical angle will also cause total internal reflection. That's why we say that the critical angle is just the minimum angle of incidence. So taking a look at this diagram one more time, the critical angle is the one that corresponds to an angle of refraction of 90 degrees. So I really want to focus just on this single beam right here that hits my surface at an angle of 48.8 degrees. That's what it happens to be for this water to air boundary. And when that's the case, my angle of refraction is 90 degrees. So using Snell's law, I would say that N1 times the sine of the critical angle, or theta sub c, is equal to N2 times the sine of 90 degrees. That would be true in general for any expression for any two mediums. If we were looking specifically with this example here, this is light that is in water first and then in air. So N1 would be 1.33 and N2 would be 1. If I were to solve this equation for the critical angle, then we'd see that the critical angle is equal to the inverse sine of N2 over N1. And that comes from the fact that this sine of 90 degrees is equal to 1. And so I would then solve for this unknown variable. This is an equation that you will be given on any assessment that we take. That was an introduction to total internal reflection and the critical angle. We'll see lots of examples and put that idea to use in several questions and problems.